Well, hello, calculus students. Yes, I said calculus. You are not pre-calculus students anymore. We are going to go ahead and finish up this 11.0 notes slash worksheet. And tomorrow, we are not going to go to 11.1. Instead, Mrs. Pinion is going to give you a Google form. She's making one for Friday. It'll be a real short, like 5-question Google form, just covering what we're covering yesterday and today on this worksheet. So we'll get to 11.1 on Monday. She'll hit limits with you on Monday. All right, but let's go ahead and get on to this. We are on number 5. So hopefully you got everything else through number 4. If you want to check your 4.99, you can. Right there is the answer to that. But number 5 says use a straight edge on the graph on the front. Construct the secant lines, which all a secant line is a line that hits 2 points. Construct secant lines through D3 to D5, D4 to D5, and D4.9 to D5. All right, so we're just going to go through the y values at 3 to 5, 4 to 5, and 4.9 to 5. All right, I've already started constructing this ahead of time, and since we're getting ready to do some calculus, better turn this puppy around. It's about to get going, baby. All right, so looking at the front here, all I've done so far is I've marked D of 3, just the y value at 3. I marked D of 4, I marked D of 4.9, and I marked D of 5. All right, now this first one, I've had this pre-constructed, is the secant line through D of 3 to D of 5. Okay, so that's given us a slope, and you already calculated that on your chart when you did the change from D3 to D5. All right, the slope of that line. All right, then we're supposed to draw a secant line through D4 to D5, which would look about like that. I'm trying to go through this point and this point here, D5. All right, and then we're supposed to do, oh, whoops. Then we're supposed to do D of, or I'm sorry, through D 4.9 and D5. Well, that is getting really close together. Okay, I mean, our 2 points are just sinking in together, closer and closer and closer. But that gives us a really good estimation of what is going on at exactly 5. And that, my friends, is instantaneous rate of change. We're trying to figure out what's going on at 5, but we can't really see what's going on at 5. So we're just going to let the number before 5 get really close to us. So that from 4.9 to 5 is a pretty good estimation of what's going on at 5. Okay, and what's happening is these secant lines are getting closer and closer and closer to being a tangent line. A tangent line is a line that hits a curve one time, and that is a derivative. A derivative is the slope at exactly 1 point. That's your first calculus concept, and it's a big one. There's only 3 big calculus concepts: derivatives, limits, and integrals. Okay, and derivatives and limits go together, and then integrals are undoing a derivative. They're antiderivatives, literally called that. Okay, but anywho, getting back to derivatives, a derivative is a slope at exactly 1 point. And if you look back at yesterday's work, well, looking at that, well, we can't figure out the slope at exactly 5. But we can estimate it really close by doing some number really close to 5 and doing that little tiny gap in between. Let me show you this because this gives you a better picture of it. I have this constructed on Desmos. What this lets me do is just get that. You can see the secant line is getting closer and closer, and as those 2 points get closer together, oh, we almost got a tangent line. Oh man, we're close. Okay, so what we're trying to do is get really close, and there's 4.9 to 5. I mean, look how close these two are together. Holy smokes. Okay, and if we get them even closer and let that gap get closer and closer and closer, oh, when it's on 5, it disappears. Well, that's because it's indeterminate at that point. But if we get really close, oh man, that's almost a tangent line. I mean, that is like right on top of each other. So that's what's going on as far as a derivative goes. When you do a derivative, you're actually letting the space between those 2 points approach zero. And that's what Mrs. Pinion is going to teach you on Monday. She's going to talk to you about limits, which let the space between two things approach zero. And that's what we're doing. We're letting the space between those 2 points approach zero. All right. So that's what a derivative is. It is a slope at exactly 1 point, and we're going to estimate it by putting 2 points that are really close together. All right. So going back to our notes here, the secant lines for 5A, they're getting closer to becoming tangent lines. And then based on the information in this table up here, give an accurate estimate for the velocity at t equals 5. Well, my accurate estimate is going to be the answer for 4.9 to 5, or 4.99 to 5, which is 45.2. And that's just the slope between these two. All I did to get that 45.2 was take 444.030 minus 443.578, and then divided by 5 minus 4.99. Just y2 minus y1, x2 minus x1. Just did slope. Okay, so this 45.2, that is also going to be my answer for down here on part B. Okay, uh-oh, my smart notebook's locking up. No! All right. So anywho, that's going to be my answer for 5B down here. There, it unlocked for me. All right. And that would be in miles per hour, because that is the rate of change. Slope is a rate of change. Okay. Now, part C says a derivative is the slope of a tangent line. We just covered that. All right. What does the derivative, which is written d derivative of t, or d prime of t, that's a new concept to you. That means the derivative of the function. Okay, that's what that little prime, that it's like an apostrophe is what we use. All right, but we say d prime, okay, or d derivative. Okay, so d prime is more common. So at d prime, that's saying my derivative. What does it represent? Is it average velocity or instantaneous velocity? Well, the answer is instantaneous velocity, because we're getting closer and closer and closer to 1 point. We're trying to find the velocity at exactly 1 point. So that's the answer to that one. All right. Now that kind of concludes the notes part. I want you to try 6, 7, and 8 on your own. Number 6 is asking you to do average velocity. So all you're going to do with t equals 1, t equals 6 is plug them into the function, get y values for each of those, and then do the slope between those 2 points. Okay. Number 7 is asking an accurate estimate for the instantaneous. Oh, the word velocity should be in there. Sorry. The instantaneous velocity at t equals 6. Well, to do that, we're doing a derivative. So we can't do 6 to 6, because then we'll get that indeterminate thing, just like we did here, when we tried to do 5 minus 5, you get 0. And if you take the y value minus itself, you get 0. You get indeterminate. So what you got to do to do number 7 is estimate the velocity at 6 by doing something like 5.99. Put that into the function, get a y value, and then put 6 in, get a y value, and then just do the slope from 5.99 to 6. Do the, subtract their y's, subtract 6 and 5.99 on the bottom, divide it, boom, you'll have a really good estimation for it for the slope at exactly 6. All right, and then number 8 asks you to do another instantaneous velocity. I'll let you tackle that one totally on your own. All right, so finish up this worksheet. You can go ahead and turn that in Google Classroom. And like I said, tomorrow Mrs. Pinion is going to post she's making a small Google form to kind of check you on this average velocity or average rate of change versus instantaneous rate of change. All right. Well, you guys have a great day, and welcome to calculus. Take care.